All right, ladies and gentlemen, so today what we're going to be working on is Coulombic attraction. So this is going to be something new that we're starting with our new unit today. So before we get started, it says that Coulombic attraction is the attraction between oppositely charged particles. So for example, the protons in the nucleus of the atom have an attraction for the electrons surrounding the nucleus. This is because the protons are positive and electrons are negative. The attractive force can be weak or strong. In this activity, you'll be exploring the strength of the attraction between protons and electrons in various atomic structures. So one thing I do want you guys to do before we even go any further is highlight this section right here about what Coulombic attraction is. That's going to be super important in all four of these pages of our POGIL that we'll do the next 2 days, as well as for pretty much everything that we're going to be doing in this unit about periodic trends. So the trends or the way the periodic table is set up, all of it has to do with this idea of Coulombic attraction, the attraction between those positive protons and the negative electrons. They're being pulled towards each other and what that does for our atoms. So if we look at this first picture,
That's a hole right there. So funny.
So if we look at this first picture, this model 1, it says it has a distance and an attractive force. So if we're looking here, we have this positive side. What do you think this positive side represents? If we're thinking about our atoms, what does that positive represent?
Protons.
Protons, perfect. So then the negative over here is going to represent what?
Electrons.
Electrons. Awesome. So there's a distance between those protons and electrons. It's for this first one, letter A is 0.10 nanometers. And just to give you reference as to what that means is 1 nanometer, or I'm sorry, 1 meter equals 1 with 9 zeros. So 1 billion nanometers. So a nanometer is really tiny and it's 1/10 of a nanometer. So just imagine how small that is. And that's the distance between our protons and our electrons. That's why they're so tiny, is because there's such a small distance. But compared, they are getting larger from A to C. If we look over here, do you guys know scientific notation? So that times 10 to the negative 8th power. Do you know what that means? Do you guys know what this section means right here? This times 10 to the negative 8th power. So that times 10 to the negative 8th power really means that you're taking that decimal point in this 2.30, you're going to move it to the left 8 times. So that negative tells us we're moving it to the left 1, 2, 3, 4, 5, 6, 7, 8 times. We're going to put it here. So that means we're going to add a 0, and 0 for every spot we moved it over. So 0.0000, lots of zeros. 230 is our force. So it's a very tiny force, but it's going to get even, if we look, it's getting even smaller because it went from 2.30 times 10 to the negative 8th to 0.58 times 10 to the negative 8th to 0.26 times 10 to the negative 8th. So it's getting smaller as we go down. So it's getting smaller. So we've already answered that first question. The positive represented what?
The electrons.
The positive or the negative?
The positive.
Try one more time.
Protons.
Oh, never mind, never mind.
The positive is going to be our protons. The negative is going to be our what?
Electrons.
Electrons. Awesome. So we got our protons, we got our electrons. And so now our next step is, next question says, would you expect to observe attraction or repulsion between the subatomic particles in model 1? So do we expect that those two are going to attract towards each other, or are they going to try and get away from each other?
They're going to attract each other.
They're going to attract towards each other because we know that Coulombic attraction, meaning that the protons and electrons are attracted. So attract. So we'd observe attraction here. Number three says if the distance between protons and electrons is 0.5 nanometers, would you expect the force of attraction to be greater or smaller than that 0.26 times 10 to the negative 8? So let's look back up at model 1. And if we look at these numbers, we went from 0.1 nanometers to 0.2 nanometers to 0.3 nanometers. So is that distance between our protons and electrons getting bigger or smaller?
Bigger.
It's getting bigger when we go between the two. When we move down, the distance is getting bigger. And we already wrote down that our attraction force is getting smaller. So if we make this an even bigger distance, so we have our proton over here and our electrons way over here, do we think that it's going to be less than or greater than this 0.26? And I had somebody already answer that. Anybody else want to give it a go? So if we're at 0.5 nanometers, so it's even farther apart, our attractive force is going to be smaller than 0.26 times 10 to the negative 8, because it's getting smaller as our distances get farther away. So it's going to be less than. So now the next question says, if two protons are 0.1 nanometers away from one electron, would you expect that force to be greater or smaller? So if I put a second proton over here, so I have two of them, I have a bigger positive force or bigger positive side. All right, I got one person saying an answer. Anybody else want to go for it? All right, it's going to be greater than. So the more protons, the more positive, then there's going to be a larger pull on those electrons to get them closer. So it's going to have that greater force, or it's going to be a larger number than the 2.3. And then the last one we're going to do together, and then I'm going to kind of let you go on your own for the next couple pages, is circle the correct choice. The closer the protons and electrons are, the stronger or weaker the attraction is. So what do we think? Do we think it's going to be stronger, or do we think it's weaker? Why don't you guys send me a
Stronger.
Oh, even better. Perfect. So it's going to get stronger. So the closer they are together, the stronger the attraction is going to be. Because they're closer, that attraction is going to get larger. So now for the next 2 pages, because you're going to stop after page 3 for today, the next 2 pages, what you're going to do is use those models to answer the questions. So this one says model 2, the alkali metals. So the diagram shows the attraction force for lithium, sodium, and potassium. Determine the atomic radii or the atomic radius. The atomic radius is the distance between the element's nucleus and the outermost electrons, or those valence electrons. So the atomic radius and Coulombic attraction are going to be indirectly related. So if we look at that picture before I let you guys move on your own, the bigger or the wider the arrow, so the bigger or wider the arrow, the stronger that attractive force is. So which one of these has the strongest attraction between its protons and its electrons?
Lithium.
Lithium has that strongest attraction because it's got the biggest arrow. So that means potassium with the smallest arrow has the least amount of attraction between these three elements. Now what your job is to try and answer questions 6, 7, 8, 9, 10, and 11 for today. So you're going to stop before you get to model 4. You're going to try and answer those 5 questions.